Good morning, and thank you again for coming out to the the 2011 Clean Tech to Market Symposium. My name is Mike Perez, and standing to my right are Stephanie Green, Edward Lee, and Antoine Caval, and together we are the carbon sequestration team. Over the course of the last semester, we've had the privilege to work with Drs. Ronald Zuckerman and Chunlong Chen at the Lawrence Berkeley National Lab to develop a market assessment report for a new type of carbon sequestration technology currently under development at Lawrence Berkeley National. Today, what we'd like to do is take you through an overview of that technology, discuss some of the potential market applications of that technology, and then discuss some of the challenges and opportunities for further research going forward. But before we do that, I'd like to take a few moments just to give you an overview of why carbon mineralization is so important, particularly with reference to the current dominant form of sequestration, geologic sequestration. Geologic sequestration requires the capturing of CO2 from a point source emitter, the transport to a geologic site, and then the injection as a gas into some sort of underground reservoir. One of the prime concerns about geologic sequestration is the risk of leakage, either into groundwater sources or back into the atmosphere. This is where carbon mineralization shows its first benefit. Carbon mineralization takes the carbon dioxide and sequesters it in the form of a solid, a mineral, in our case, calcium carbonate. The second benefit is that that same mineral that safely and permanently stores the sequestered carbon can be used to potentially create carbon neutral or carbon negative products. By attaching some sort of process to, say, a cement factory, you could actually use the CO2 that comes from the cement factory to create the exact mineral that is one of its #1 inputs. In addition, and as carbon capture kind of alluded to towards the end of its question and answer period, there are many suitable geologic sites for geologic sequestration. However, many of them are not hooked up to the pipeline system that we currently have. So one of the beauties of carbon mineralization is that you can actually sequester carbon on site at a point source emitter and avoid the costs of building further pipelines or any sort of trucking that might take the CO2 to one of those geologic sites. Now with that, I'll turn it over to Antoine to tell you a little bit more about the technology.
Thank you, Mike. So I'm going to give you an overview of our technology that is called the peptide technology. So first of all, what are peptides? Peptides are a novel class of non-natural polymer that can mimic the properties of enzymes. They are created thanks to an automated synthesis that enables scientists to obtain a vast collection of compounds with a really specific defined sequence. So then a screening process is conducted in order to select the peptide that exhibit a specific and interesting biochemical activity that can be used in a wide variety of applications, such as inhibitors, antimicrobial agents, cancer therapeutic, and catalysts. In our project, we focused on using peptides as catalysts in carbon mineralization, and our process, which is based on this reaction, requires 3 inputs. First, calcium ions, CO2, and a source of alkalinity. And this process turned this input into calcium carbonate minerals. The benefit of using peptide technology in this process are, first, it significantly speeds up the growth of crystals. Additionally, we can use a dilute source of inputs, which can potentially broaden the sources of those inputs. We are also using really small concentrations of catalyst and are able to reuse it over many cycles. And so this represents a great opportunity for us to drop the cost of our technology down. Finally, we are producing the most abundant form of calcium carbonate that is used in a wide range of industrial applications and that brings value to our end product. So now I would like to present you the major challenge we are facing with our technology right now, and that is linked to, that is related to the CO2 balance of the overall process we're considering. We are currently using sodium hydroxide as a source of alkalinity, and because this compound is highly reactive and is not naturally available, it requires an extremely energy-intensive process to be produced. As a consequence, because we are using this energy, we are basically creating more CO2 than we are sequestering with our process, resulting in net CO2 emission. So there are two strategies to overcome this challenge. The first one is to look for another source of alkalinity, a one that requires less energy to be produced or that is naturally available at a sufficient scale for carbon sequestration. However, based on the insight of both academic and professional experts in carbon mineralization, we strongly believe that this solution is highly unlikely. So we recommend a second strategy, which is to rely on the versatility of our technology and adapt our peptide catalyst to a new chemical reaction. And again, based on the feedback received from this expert, we strongly believe that peptides can have a significant positive impact on processes that uses silicate rocks as a source of both ions and alkalinity, and that would result to a net CO2 sequestration. So now I'm going to turn it over to Stephanie that's going to talk to you about potential application.
Thanks, Antoine. So we identified two main commercial applications for our technology. The first we call above ground. So that's essentially taking a power plant that's currently above ground, sticking our technology onto it, and sequestering carbon on site at that power plant. There's a variety of different options here. I'll talk about those in more detail in the next slide. The other option is to complement geologic sequestration. So that would be taking existing geologic sequestration sites, sticking our technology underground, and using it to speed up the mineralization process that's happening in those sites. So looking at these opportunities in more detail, the first is we could potentially bypass the entire carbon capture process. Now, I'll say this with the caveat that our technology is still quite lab scale and needs further testing to ensure that we can actually use flue gas as an input, but we believe that it can be used as an input, and that means that we can literally take flue gas or take natural gas output and use it to immediately sequester carbon dioxide right there into a mineral form. So this would essentially take the carbon capture and storage CCS process and turn it into a single step. So as Mike mentioned, some of the benefits from this, first of all, are we could avoid the construction of new pipelines. So most power plants right now, some of them are located on existing pipelines, but some of them aren't. So we could avoid new pipeline and CO2 transport costs. In addition, we could avoid just all of the extra costs that come from a separate capture step. We also believe this market's quite large and in the future is expected to grow 1 to 2 gigatons of carbon dioxide per year. Sorry, it's not growing, but that's the ultimate size of the market expected by many experts we spoke with. So secondly, either in combination with bypassing capture or as a separate step, we could sell our calcium carbonate output. And again, this has the value, as Mike mentioned, of having a carbon negative product. While this market's a lot smaller than the overall carbon capture and sequestration markets today, we still believe it has the potential to significantly improve the economics of our product. So the key challenges of both of these market areas include finding an alkalinity source that, as Antoine mentioned, that is not so energy intensive and that has lower costs, and also the overall cost of our process. So when talking more about selling our calcium carbonate output, you'll see that there's actually a large number of industrial users of calcium carbonate. These are just 4 of them. And what's great about this market is twofold. First, these are large users. They use a lot of calcium carbonate. The second thing that's really great about this market is that they're all very carbon-intensive industries. So they would find value, in particular with potential carbon regulation, of purchasing a carbon-negative product and then using it in their outputs. So the third option is we could complement geologic sequestration. So as I mentioned before, that would be taking our technology, putting it underground, and using it to speed up the existing sequestration process. So this would ensure a safe and stable form of sequestration and would avoid monitoring costs that come. Right now, most sites require 50 years of monitoring to ensure that the carbon doesn't leak. So this would save a lot of those time and efforts. The key challenges here, again, are that it's a relatively small market today, but in the future, it could be quite large with regulation. Another main challenge, though, and it turns out that we found that this is such an issue that we recommend not pursuing this market further, is cost. So to dive into that a little deeper, so the overall CCS process, as you can see from the left bar graph here, is on average around $100 per ton of carbon dioxide right now. And of that, in the orange bar, only a very small part of that is sequestration. And in particular, only 50 cents per ton is monitoring cost. So we feel that if we cannot bypass the capture process in addition, it doesn't really make sense to simply complement geologic sequestration. We really need to replace geologic sequestration and replace that capture process. So on the right-hand side, you can see the cost of our catalyst today. And I repeat, this is lab scale. There's a lot of different question marks about these cost analysis. But on average, the cost is upwards of around $260 per ton. However, if we can sell our output, the costs become a lot more attractive. And we believe with efficiencies achieved at scale and further development and refinement of how much our catalyst can be reused, we can bring these costs down to be almost competitive with CCS technologies today. Now I'll turn it over to Edward. He'll talk about the operating environment.
No, I've got the
You don't have this.
All right, so in looking at the competitive market, what we've done is separated our competitors in two segments. The first segment being those producers who incorporate some type of carbon negative process as part of their production. And you can see that's in the first two columns. The second segment is traditional producers of calcium carbonate. Those are typically multinational chemical companies that have been doing this for a while. Oops. What we've, in terms of our focus, we believe that our technology should be geared towards addressing those competitors that are in the carbon negative process space, and for a couple of reasons. First of all, in terms of the value proposition of our technology, we believe that the ability to offer a carbon sequestration and carbon capture process is quite valuable. And the second point is that from a cost perspective, we believe that those companies that engage in traditional production processes and focus this as a pure play type of process are likely to have a lower cost structure for a number of reasons. First of all, in terms of their ability to incorporate the knowledge that they've developed over a number of years, and secondly, they don't need to have regard to the carbon sequestration and carbon capture processes. So what does that mean in terms of our technology? We've come up with a couple of conclusions. First of all, the carbon mineralization market appears relatively open. As you saw from the previous slide, there are only a handful of competitors. And at this stage, all of them are more or less at the lab scale, or if they have progressed beyond the lab scale, they only have one or two commercial plants. The second point is that there appears to be demonstrated financial support for these types of companies. The DOE have been supportive of New Sky Energy with a $25 million or so grant in the last year, and the VC community has made an investment as well in this space as part of Kilera. And the third and final conclusion in terms of the competitive framework is that while the cost equation remains very important, we've found it quite difficult to get some transparency and clarity around the cost structures of our competitors. As you would expect, our competitors have been a bit secretive in terms of giving us the costs of their production processes. And so we would need to further understand these in terms of moving forward. And now Mike is going to talk a little bit about the regulatory process.
Thank you, Edward. So as the carbon capture team alluded to earlier, we are seeing some great moves towards a more regulated carbon market, but as it stands now, it is somewhat fragmented. As we began our research into carbon mineralization, we realized very quickly that in order to make accurate assessments and accurate recommendations going forward, we definitely need to look at the regulatory environment. So we looked both internationally and domestically. In the international market, we're seeing sort of a top-down approach to carbon regulation. At the top, we have the Kyoto Protocol, which sets emissions reduction targets for countries who have ratified that protocol. From there, it's up to those countries to decide how they're going to meet those target emissions. And here we see a plethora of innovation in how they're going to do so. So, for example, there's a multinational agreement called the EU ETS, or European Emissions Trading Scheme, that comprises of the European nation to meet those targets. There are national schemes, such as the New Zealand Emissions Trading Scheme. Then we get even smaller, and we have state-level schemes, such as the New South Wales Greenhouse Gas Reduction Scheme, and even the Tokyo Metropolitan Government's cap-and-trade scheme. So we see a very top-down push to make sure that these carbon regulations happen and meet those goals. Here at home, we have the opposite effect. At the federal level, we don't see much in the terms of carbon regulation. We do have tax incentives. IRC Section 45Q offers up to $30 worth of incentives for geologic sequestration or enhanced oil recovery. But it's actually the states that are acting as the laboratories of innovation in this area. So in the Northeast and Mid-Atlantic region, there are 10 states that have engaged in the first mandatory cap-and-trade system called the Regional Greenhouse Gas Initiative. Some states offer what are called VERs, or voluntary emission reductions credits. These are credits for people who are currently voluntarily sequestering carbon dioxide in case some sort of regulatory framework does show up in the future. And states like Oklahoma have set up carbon sequestration funds to actually have state funding for the future of carbon sequestration technology. So again, much like the latest addition to the Clean Air Act and regulation of automobile emissions, we're seeing states taking the forefront in making these regulations happen. And just as the carbon capture team said, going forward, it's not if, but when these are going to take place. So now that we're looking forward, it sounds like a good time to summarize where we've come from. On the technological side, again, we've recognized a number of challenges. The four main opportunities for research in the future being checking to ensure that CO2 flue gas can be used in order to reduce the cost structure, finding a source of alkalinity that is more conducive to large-scale or commercial-scale production, testing to see how many times that catalyst can be reused so that we can also, again, take down the cost at scale, and finally, correcting that overall energy balance. And again, to repeat, our two solutions here are either to find a different source of alkalinity for the current reaction, which seems improbable at this moment, or move towards a new reaction, one such as the one on the right, for example. This reaction uses silicate rocks. It's a three-step process. You dissolve the rock. That provides both alkalinity and sources of ions, thus tackling two of the original problems we had. Then you dissolve CO2 into water, and then using some form of our catalyst, reprecipitate it back into a mineralized form of carbon to permanently sequester. Right. And now I'll turn it over to Edward to take away our commercial takeaways.
All right. So in terms of, from a commercial perspective, we've made the following conclusions in respect of our technology. The first is that we believe that there's a potential opportunity from a commercial perspective as an alternative to geological sequestration rather than complementing geological sequestration for the reasons that Stephanie outlined earlier, but principally cost. The second conclusion we would make is that being able to address some of the technological challenges that we've identified, as well as the ability to move from lab scale to more commercial scale is critically important. And many of our competitors are in that stage of their process, and so that is a key issue that needs to be addressed. The third is that, as Mike identified earlier, there are some challenges in terms of the regulatory environment, and it appears that moving forward, the regulatory environment looks to be increasingly positive. So in terms of the way forward, we would conclude that the immediate focus should be on the technology and addressing some of the challenges that my team has discussed today. We feel that the key focus should be ensuring that it's fit for purpose, as well as ensuring that it achieves bare minimum cost. After we address these concerns, we feel that moving forward, we should be looking at ensuring that we are able to match our technology with a market, and then the next stage is to explore commercial opportunities connected with the newly developed technology. And so at this stage, we'd like to thank you and open up the floor for questions that you may have.
I guess when I look at a market, my big question is, why do you sequester any of this at all? In other words, if you can basically, and one thing I didn't see, which was the supply-demand balance between users and suppliers of CO2. I think that would be a benefit to all of us to say, you know, if there's a user group out there for CO2, why not just plant the user next door to the flue and basically do it as we used to call it, cogeneration. So fundamentally, I'm not clear as to why we need to mineralize anything at this point if we can find a user that could be next door and fundamentally take the tap, take that CO2 and use it for their purposes. So that's kind of my overriding theme here, is why this technology at all?
That's a great question. Some of the sort of overall rationales and importance for this technology we left in some ways to the carbon capture team to sort of say what's the overall size of greenhouse gas emissions. You know, we have many of the same numbers of them. Our understanding is that, sure, there are a lot of users of CO2, but they're not nearly large enough to encompass the amount of CO2 that we need to achieve climate stabilization targets as needed going forward. And so you're right, you know, we do actually have those numbers. We didn't present them today, but we personally believe that it's just simply not, the pure CO2 market is simply not nearly large enough when we're talking about the scale of global warming that we need to address here.
Very nice job by the team. And were you going to add something further? I see you look on. Anyway, I'm here. I'm your stealth questioner. It's just a big voice. So actually, I was confused by one thing, and this probably goes to Antoine. You talked initially about the calcium carbonate process, and then you dismissed it somewhat because of the issues of the cost of the lye, the sodium hydroxide. Pardon me, by the way, it's been a long time since I took a chemistry class, so if I get my minerals wrong, excuse me. But it looks as if your recommended process is a magnesium carbonate-based process. And unless there's a third step, I don't see any calcium carbonate coming out of that recommended process. And therefore, the big question mark for me is, what is the market for the magnesium carbonate, and how does that compare to the calcium carbonate?
Okay, thank you for your question. So this reaction that we presented you with the magnesium silicate comes from a researcher that is working currently in this process at Columbia University. And this person told us that it is possible to do that with calcium silicates, which is approximately the same that magnesium silicate. The only thing is that magnesium silicates are really much more abundant in rock forms. So they are focusing on this potential equation because of the availability of magnesium silicates rocks. As for the market application of magnesium silicates, because we focused only on magnesium carbonate, because we focused only on our output, there is a market for magnesium carbonate, which is really smaller than calcium carbonate because of the availability of calcium carbonate at a natural form, at a natural source.
And I'd just like to add something for full disclosure here. So we spent many, many months studying our existing chemical process that you saw on the left. And it was only towards the end of our entire research process that we determined some of the technological issues that you saw today. So, we did not have the time or ability to really research some of those alternative equations in the same detail that you saw for our equation, our original research equation.
I think you did a great presentations. I have a question. Did you look at the use of calcium carbonate as pretreatment for lignocerrosic biomass ethanol? Because they want to use limes, and it means it will be a huge market to convert to.
I'm so sorry. Can you repeat that? Did we look at researching it for what?
To use calcium carbonate as pretreatments. So if you look
as pretreatment for
biomass conversion to sugars, and that you can convert this to biofuels. Because the market there, if it's moved forward, will be very huge. And another question is, for farmers, they are also applying calcium carbonate on the fields, and also they use a lot of potassium. And could you use also potassium hydroxide instead of sodium hydroxide to use to do for your reactions?
So I'll just address the market once. Antoine will talk about potassium hydroxide. Just to answer your questions really quickly, those were just examples of industrial users of calcium carbonate, and you're right, there are many other opportunities. We felt that those stood out because they make building materials and other things in the built environment. But we agree, it's quite a large calcium carbonate market, and there's a lot of opportunities we did not explore today.
So to clarify your question, you are asking if we would be able to use the potassium hydroxide. So the potassium hydroxide actually have exactly the same problem as sodium hydroxide because it has to be produced thanks to an industrial process, and that requires basically the same amount of energy. So we really have to find a source. Our process is not running at high pH, so we just have to find a source of alkalinity that enable us to have a large scale of alkalinity in order to run on process. And we can't rely on traditional bases such as ammonia or potassium hydroxide.
You looked at the end, it looked like magnesium, was it carbide? That was your preferable method, the magnesium? Okay. Have you looked at how you could break that out to straight magnesium? The reason I asked that is there's a huge demand for magnesium lightweight materials in the automobile industry. Have you looked at whether you can break that down into magnesium and be cheaper than some of the super steels and things that they're looking at? They're looking at a market of, 60, 80 million vehicles a year worldwide.
Yeah, I must say we have not looked at that yet. That's just one example of one possible equation, but it would definitely be, it definitely sounds like it would be something we'd be happy to look into. Anything to make it, this technology get to market sounds great.
Oh, yeah. I have another question. Have you looked at the volume of calcium carbonate, for instance, that can come out of a coal-fired plant when you actually would hook something like this up to it? I mean, I think from rough calculations, it adds up pretty quickly. So you just have mounds and you have mountains that you're making in no time. So I don't know how you deal with these mountains. That's just one question I have for this technology. So.
Yeah, no, we did look at that, and I think I sort of briefly mentioned that when I said the size of the calcium carbonate market is significantly smaller than the size of those markets, and so it's a challenge. We would probably have to incorporate transport costs or putting it underground to an extent or dumping it in a landfill. We would have more calcium carbonate than we would be able to sell.
I mean, it's the same problem with, like, desalination plants. When you're left with the brine, what do you do with it? And those are big problems. I think that's what has to be addressed if you wanted to really consider a technology like this.
Yeah, no, thank you for that. We definitely agree.
Great. Well, thank you, Carbon Sequestration.